Chaos. What do you imagine when you hear that word? Explosions, war, supernova, primordial wastes with volcanoes, hurricanes and tornadoes tearing apart the landscape. Perhaps instead, you imagine a still and lonesome desert. A gentle breeze through trees, a wave slowly lapping onto the beach. No? Each of those scenes makes up a part of our universe, and everything in the universe makes up chaos theory. But what exactly does that mean? Chaos theory describes how tiny, almost unnoticeable effects on the initial conditions can have drastic, life-altering effects on the outcomes. The most popular version of this is known as the butterfly effect. Say, in London, there's a butterfly sitting on a flower collecting nectar. It's a completely normal day. Everybody just goes about their business, probably don't even notice that the butterfly's there. Once the butterfly's finished, spreads its wings out large and flaps. That might be the end of it, if it wasn't for the tiny effect that had on all of the particles around it. All of those tiny molecules have just been shifted ever so slightly out of place by that wing's movement. And so, it creates a vacuum, and all of the particles around that start moving in to fill that space. But then that leaves another vacuum where those particles were. So the particles even further away then move even further in. That tiny movement of the butterfly's wings creates a ripple effect, moving all around the Earth's atmosphere, shifting everything just a tiny amount. But perhaps in one area that ripple's a little bit stronger, and you get a slight breeze, maybe even stronger than that, and a sudden gust takes someone's hat off. Or you can have hurricanes and tornadoes, all kinds of chaos. This is the first topic that I want to talk about, and I think it's perfectly fitting. I was recently on a hike with a friend, and I brought up that I wanted to start making videos like this, talking about really interesting topics, but also talking about how it affects our daily lives. But I just didn't know where to start. They told me, and I'm paraphrasing this just a little bit, just start. Just make something, and maybe you'll hate it, maybe you'll delete it later, but at least you'll have made something. And then you can just see what ripples out. So, I'm starting here. And maybe nothing will come of this, or maybe everything will. And that's chaos. The first writings which discuss topics that would eventually become chaos theory came in the mid-19th century by James Clerk Maxwell. Maxwell is most well known for the eponymous Maxwell equations, which discuss the links between electric and magnetic fields. But he also did a lot of work on how initial conditions affect the outcomes. At the time, Maxwell was working on deciphering equations that would eventually discover the motions of a gas, work that would eventually become the Maxwell-Boltzmann distribution, but I'll talk more about that at a later date. During his research, Maxwell found that how the gas particles interacted depended greatly on the initial conditions of said gas particles. So, imagine you have two particles that are assumed to be spherical, they have about the same mass, and are travelling at about the same speed. If they collide, Maxwell found that they had an equal chance of going off in any direction. Overall, this averages out, so it wasn't super important for what Maxwell was trying to work out. But it did open his eyes to how ever so slight changes in what you assume to be perfect actually create massively different systems. One day, Maxwell was giving a lecture at Cambridge University, and he said a somewhat famous quote, When an infinitely small variation in the present state may bring about a finite difference in the state of the system in a finite time, the condition of the system is said to be unstable. They didn't have chaos just yet. In the 20th century, chaos began appearing a bit more frequently. Radio engineers encountering static for the first time tried to plot it so that it could be removed from their general transmissions, but found that it was so entirely unperiodic, it was completely random. This static was, and still is, caused by a plethora of different sources, from things like lightning strikes to the background radiation of the universe to even small things like the slight change in movement of molecules in the resistors of the radio itself. Tiny little differences that resulted in a completely incalculable noise overall. So, it was here to stay. With the invention of computers, mathematicians really tried to calculate chaos. The previously lengthy and difficult to understand equations could be easily handled by computers and then outputted into easy to understand things like images. This is most prevalent in weather forecasting. Weather forecasting in its most basic form has been around since ancient times, but back then it mostly consisted of just analysis of clouds. The different cloud formations were noted every day. So if one day you had a certain cloud and the next day it was really stormy, that meant for ancient meteorologists that if you ever saw that cloud again, you'd know that the next day would be really stormy. And the majority of the time they'd be right, but it only meant they could predict about a day in the future. Fast forward a few thousand years, and inventions like the telegraph allowed people to note the weather across continents. Then the weather could be collected and studied by meteorologists to find out what weather in one place might cause the weather in another place. This allowed meteorologists to see weather fronts and effectively know where weather was going to head next. It worked most of the time, but only on existing weather fronts. If clouds suddenly formed or decided to fizzle out, meteorologists would be none the wiser. Once again, with the advent of computers, meteorologists were able to input tiny values to know where clouds were headed, if they were going to form or if they were going to disappear, thereby allowing us to have much more accurate weather forecasts. And that should have been it, if it wasn't for this graph. This graph shows the weather forecasting accuracy of the last 50 years or so. Whilst, in general, the overall accuracy of their predictions has increased, the same rules still apply back then as do now. The further forward you try to predict, the less accurate you're going to be. And the reason for this? Chaos. There are so many unpredictable factors when it comes to weather. How much evaporation occurred to allow the clouds to form, how the wind will decide to blow to move weather fronts in different directions, how much water will decide to collect at the bottom of a cloud so that it will rain, and so on and so on. There are so many factors, and even a slight change to one of these would mean completely different weather for thousands of people. These days, with our very impressive computers, we can predict weather up to 3 days in advance with an almost 100% accuracy. But try to look 10 days in advance, for example, and that accuracy falls to be around 50%, which means they're only getting it right half of the time. When it comes to chaos and how it affects us, we still have quite a long way to go. But we've also managed to tame a lot of it, figure out the tiny little equations that govern so much of our everyday lives. And we're still going. Chaos theory isn't just present in physics. It's often used in media as a literary device. The most well-known example of this is probably the butterfly effect, starring Ashton Kutcher. In the film, Kutcher's character Evan finds out that he can time travel to different events in his life and change their outcome. This sometimes leads to small changes, like him having a scar where he deliberately hurt himself, but more often leads to bigger changes, like him now dating his crush, or his best friend going insane after accidentally killing someone. The film shows really well how small changes in the initial conditions can lead to massive changes in Evan's later life, as well as the lives of everyone around him. This is perfectly summed up in the film's slogan: change one thing, change everything. On the opposite end of the spectrum, in the book and film Jurassic Park, Dr. Ian Malcolm, played brilliantly by Jeff Goldblum, uses chaos theory to describe how, even though the park security think they have everything under control, chaos can come from even the slightest thing going wrong. This is eventually shown to be the tiny DNA fragments of certain frogs, which have the ability to change sex. This then allows the dinosaurs to change sex, breed, and eventually overrun the park's security. The next piece of media that utilizes chaos theory is one that's really close to my heart. Life is Strange. Life is Strange is a 2015 video game developed by Don't Nod Entertainment and published by Square Enix. The game takes the idea of the butterfly effect as literally as it could. Similar to the butterfly effect film, the game's main character, Max, finds out that they can time travel to different events in their life, either by directly rewinding for a few minutes, or by looking at the pictures she takes with her Polaroid camera to go back a little bit further. The gameplay involves the player making choices regarding the events and residents of Arcadia Bay. Max can choose to be nice or mean, to save lives or to let people die. If the player makes a choice that they didn't particularly like though, they can simply rewind time and make the choice differently, so the ending is completely up to them. The game takes place over the course of 5 days, with Max discovering her abilities on the Monday and the town being destroyed by a hurricane on the Friday. The player, through Max, is working to unravel the secrets of the town and find a way to stop the storm before it destroys everything. A spoiler warning here for anybody who wants to play the game for themselves. I'll give you a few minutes to skip ahead. I'll put the time code here. Okay? So, at the end of the game, it's revealed that the storm is actually caused by Max's meddling in time. Her saving the life of her best friend Chloe on the Monday is what actually results in the storm happening on the Friday. Max then has one final choice to make. Either let the town be destroyed, or go back in time and let Chloe die. Chaos theory is very apparent in this game. Saving Chloe's life resulted in a butterfly effect, rippling throughout the town and eventually resulting in this storm happening. But similarly, there are a bunch of smaller butterfly effects throughout the game that the player can be involved in. Throughout the game, Max runs into a fellow student, Alyssa, who is constantly being hit by things that people either throw or are just sort of generally projectiles. Max can choose to warn Alyssa before it happens by rewinding to before it happens, or she can simply choose to let Alyssa be hit. If Max chooses to help Alyssa out, then at the end of the game, Alyssa returns the favor and helps Max. But if you don't help, then Alyssa won't help you. Most importantly, Max can choose to save the life of her friend Kate, another student at Blackwell Academy. Kate is suicidal after some relentless bullying from the other students at the academy. If you fail, then Kate isn't seen for the rest of the game. But if you succeed in saving her life, then Kate begins to help Max with her investigation, and by the end of the game is a much happier person. I've played through this game I think 3 times now, and each time I discover more things that completely change my opinion, how I see everything that happens in the town. The first time I played the game, I was sort of speedrunning, so I missed a lot of the interactions with the other characters, and mostly just did the things with Max and Chloe. by the time I got to the end of the game and had to make the choice between Chloe and the town, the choice seemed obvious to me. Obviously I'd pick Chloe because that's who I'd spent all this time with. But then the second time I played through the game, I really wanted to see everything else that was going on. So I talked to all the people, I had all of the different cutscenes, I made sure to take pictures of everything I was told to. And then by the time I got to the end of the game, the choice seemed obvious again, but this time in the other way. That, I think, is the ultimate showing of chaos theory that the game portrays. Nothing in the game, but how it affects you. Each time I played the exact same game, it was coded exactly the same, so I was doing pretty much the same experiment. But by interacting with it differently and by seeing different things, I changed my own initial conditions, and thus by the time I got to the end of the game, made a completely different choice. It's one thing to just describe chaos and show you a few pop culture references, so I thought I'd make it a bit more interesting and show you a bit of a real-world scenario using one of these. A pendulum. A pendulum is quite simply just a mass attached at length from a pivot. So, this very simplistic build with literally just a mug attached to a string will work perfectly. Pendulums are used for many different things, like timekeeping or detecting earthquakes or even stabilizing tall buildings. Their predictability is exactly what makes them useful. The equations of their motion have been known since the time of Galileo in the 1600s. Those equations are exactly what we're going to use. In a simple pendulum, there are only three forces acting: gravity, tension, and centrifugal force. Now, for those of you who aren't very scientific, centrifugal force is pretty much the force that you feel when you go around the corner in a car. It's sort of something that's trying to keep you going in the same direction you were going, but because you're turning, it creates a force. In the case of our pendulum, the tension and the centrifugal force act in completely opposite directions. So the centrifugal force is just cancelled out by adding a bit more tension in, so it can be ignored in our simple pendulum. The remaining tension is there to counteract the gravity that's trying to pull the mass downwards. But because it's acting at this angle, some of it is acting upwards and some of it is acting sideways. And this sideways is what creates the pendulum motion. This lateral force, known as a restoring force, is dependent on this, the angle at which the pendulum is to a vertical. And that vertical is just going in the same direction as gravity. The bigger this angle, the greater the restoring force is going to be for the pendulum. So, if you instead imagine that the pendulum is in line with this, it wouldn't feel any restoring force and would stay completely still. When the pendulum feels that restoring force, it starts accelerating towards the center. It gathers speed up until it hits the center point, at which point the restoring force is 0. So it stops accelerating, but it already has speed. So rather than stop here, it continues moving up here. Without any kind of resistance, the pendulum will swing back up to where it began. And then the whole process starts again, with the restoring force now acting that way and moving it towards the center again. It picks up speed, goes way past the center point, and back up to where it started. And back and forth, and back and forth, and back and forth. So that's a single pendulum. Quite simple, really. So let's make things a bit more complicated. This is a double pendulum. The first single pendulum with another pendulum attached to the bottom of it. You have the same forces like tension or gravity, but you also have a little bit extra. See, the tension here pulling this pendulum towards this pendulum is also acting in the opposite way, pulling this pendulum towards this pendulum. And that makes things very complicated. See, whilst both of these pendulums are stuck together and thus have to move together, they're both completely free to move around their respective hinges. So you get some really strange movement. Unlike in a single pendulum where the centrifugal force could just be cancelled out by the tension, the centrifugal force of this lower pendulum is now acting towards the top hinge, and so can't be properly cancelled out by the tension without causing way more problems. As much as I'd love to work out all the maths of this myself, it's already been done, so I'm just going to be using that. And so now, let's see it in action. So, I'm now here on my computer, where I've written a quick code to just create a pendulum, and then I've got some equations that I'll input the physics, so then everything will work just like a real pendulum. So let's take a look. You can see I've got the angle of the pendulum pretty high just to kind of demonstrate it. So it starts up there, it speeds up towards the center, and it's got such a high velocity that it carries itself all the way back up, and then the cycle continues on and on and on. For all of this code, I'll leave it in the description if you want to download it and take a look for yourself. You can change the angle, you can change the gravity, you can change anything you want. So, what I've got now is a bit more complicated code. This is for a double pendulum. So, I now have to take into account things like the masses of the pendulums. I have to take into account both of their movements around their respective hinges. And the result is this. Another extra thing I added in is something that tracks the path of the bottom pendulum, because what it creates is this beautiful picture of the chaotic motion that the double pendulum creates. You see, it never repeats the same pattern, it's always just moving this way and that way. It's completely unpredictable. And that's the double pendulum. At this point, if you're still here, and thank you if you are, you're probably wondering to yourself, Cassie, Cassiopeia, the lesson was interesting, but what's the point of any of this? And the answer to that harks back to what I said right at the beginning. Chaos is everywhere. Have you ever gotten out of the wrong side of the bed and found yourself just in a bad mood? And then throughout your day it feels like everything's going wrong and it's just making you feel worse, and you think, I was already in a bad mood and now I just feel awful. Or conversely, have you ever started off feeling bad and then as the day went on, kind of nice things happened to you, and by the end of the day you're feeling alright? It's all because of chaos theory. Your mood, how you interact with the world around you and how the world around you interacts with you, creates an initial condition that then ripples out to everything that happens. So, even if you start off your day what you think is exactly the same, depending on these random conditions, the day can go completely differently. Sometimes it can feel like you're living the same day over and over, that you're just a simple pendulum swinging back and forth from sleeping and eating and going to work and watching Jurassic Park again for the plot, but you're not. You are a complex and chaotic thing in the best way they can be, and all you have to do is change one of those little initial conditions, do anything at all slightly differently, and the whole world can change around you. Because if a butterfly can flap its wings and create a hurricane, then just imagine what you can do. So this is me, taking off. Bye.